Hi, everybody. This is Mike. Welcome to week 2. We're going to start chapter 2. I encourage you to look over chapter 2 and read it in the textbook. You will gain some good insights. It'll help you with some examples. I will be showing you a different technique with regard to the graphical solution procedure. But let's get started. All right, so what's linear programming all about? I'm on slide 2. The word programming really is meant to convey something different. It's not software programming, computer programming, and so on. It's deciding what course of action we're going to undertake when we have options that are presented in mathematical models, as we discussed in chapter 1. And they are expressed only in a linear sense. A linear function is something we would have, say, that represents a straight line, as opposed to a nonlinear function might look like a series of waves. So it's very useful. It can be applied to a lot of contexts with regard to, say, examples I'm giving there in the fourth bullet. Crew scheduling, which is the type of case I told you about with regard to TSA screeners that I've used it with. Shipping, planning, refinery operations, circuit design, network design, and so on. Little background. Where does this come from? Where does linear program, where did it originate? Well, there's a fellow named George Dantzig. He was a PhD. Spent a lot of his career teaching at Stanford. And he is the acknowledged creator of the simplex method. And he developed in the 1940s, during the Second World War, a diet requirements solution that he was attempting to develop for the Army. And he had a variety of requirements for nutrition, and he had dozens and dozens of decision variables, things that had to be decided. How many vitamin A, vitamin C, vitamin D, so on and so forth that you would put into a meal. How much salt, sodium content, how much fat content. Those would be all decision variables that would come into play in a dietary application. And when they did the solution back then, they didn't have computers to do it. They used 120 person days, if you will, using hand-operated desktop calculators. And now it can be solved very, very quickly. I did post an article in 1990 that Dantzig published about some of this. You might find it useful. Last bullet, something you'll find interesting. The notion that there is an urban legend that comes from the movie Good Will Hunting. Good Will Hunting was produced around 20 years ago, late 90s, and won Matt Damon and Ben Affleck Academy Awards. And I put some links in there. Good Will Hunting has there's part of the movie clip that I have in that link. It takes you to YouTube that describes an unsolved math problem that is supposedly based on Dantzig's real-world experience in the 1930s at Stanford, where he had solved a previously unsolved mathematical theorem. And so if you watch that movie clip and maybe read that article link I have there, you'll get some entertainment value, something you can tell stories about with regard to the linear programming methods and the management science things you're learning in this class. All right, so how does this apply in the real world? Well, one contemporary application would be the Nabisco company and the way they do different types of things with regard to their manufacturing and distribution and logistics, and they try to optimize for different approaches in terms of their production equipment utilization, how they distribute their materials, so on and so forth. They have different ovens and production pieces of equipment and so on. And they've got dozens and dozens of products and facilities and plants and customer zones around the world. They've got tens of thousands of decision variables, tens of thousands of constraints that come into play. For instance, when I did the TSA screener problem, I had only 12 decision variables and 30 some odd constraints. And I'll give you some more examples to talk about that as well. All right, so let's set up some basic foundational ground rules with regard to linear programming. The idea is that we are generally trying to maximize or minimize something. There are variations where we can equal something, but generally we're trying to maximize quantity of something, and we're going to call that the objective function. So remember that every objective function is, for our purposes, is going to be expressed as a max or a min of something. And And second bullet, all LP problems have constraints. That is, for instance, with regard to, say, screener scheduling, you can only be scheduled a certain number of hours per day. There's a certain cost associated with that, and so on. When we develop solutions, whether we do it graphically, that is the manual method, or we do it using Excel, we develop what we call feasible solutions, and they satisfy all the constraints simultaneously. So there are multiple feasible solutions in some cases, many cases, but we want to develop an optimal solution. It's one of the feasible solutions that has the largest possible objective function value. So when we're maximizing, or the smallest value when we're trying to minimize. And lastly, a key element when we're doing things manually in a graphical solution method, we can only solve using two variables. We cannot, in a practical way, do it for more than two variables. We'd have to have a third axis, x, y, and z axis. We're going to stick with matters and only have an x and a y axis. All right, let's keep moving on with some of these premises. So if the objective function and the constraints are linear, we've heard there is a linear programming problem. This is a linear representation, a linear graph, a straight line. This, or curves and so on, are nonlinear. So again, when we express these linear constraints, they're expressed in different ways. They can be less than or equal to, they can be equal to something, or they can be greater than or equal to some value. All right, we're going to work on some problem formulation. And problem formulation, here on slide 8, is the process when we translate something in writing or something expressed audibly or verbally into a mathematical statement. And it takes time. We're beginners. I accept we're going to keep things simple for this class. And I mentioned last week that a problem well defined is a problem half solved, and it's certainly true here as well. To give you an example, when I did the TSA work, the problem formulation took more than 3 months for those of us working on that project to agree on the definition of the objective functions with those 12 decision variables and the 3 dozen or so constraints to agree what they were. Now there are some good guidelines on problem formulation. We're going to walk through some examples in our text on pages 33 through 36. I encourage you to please read that in problem formulation. We are going to have a problem in our next test, test 2, that will be a problem formulation setup. Okay, now on slide 9, then let's begin an example of problem formulation. Let's look at the example in our text, the par inc problem on pages 32 to 36, and we're going to set up the objective function and the constraints here. I want you to follow along in the textbook, and I'm going to recite some of these values and circumstances that the text is telling us and try to apply them here. So that's going to be in section 2.1 in the text, beginning on page 32. So the language that's used in the text informs the mathematical setup. That's what we're going to use. And when I give you a test problem like this, I'm going to have language that will be very, very clear, and you're going to have to interpret that and create the mathematical setup, the definition, the formulation of the problem. So the first thing this requires is for you to understand the nature of the problem. Sometimes that requires asking lots and lots of questions, getting clarification, and so on. Again, when we do it in the test, I'm going to keep it very simple and straightforward. In the real world, it's not always so, and that's why it took us 3 months to do it with the TSA work. So the second step that we really should follow is to describe the objective function. Use, again, always as a max or min. Don't ever forget that, please. Don't give me an objective function that doesn't have a max or a min. Third, we're going to define the decision variables. We're going to keep things simple. Again, I mentioned that in the case of Nabisco, there are thousands of decision variables. In the case of the TSA screeners, there was a dozen decision variables. We're going to keep it simple. We're only going to have 2 for our class, and both when we do because of the graphical solution constraints as well as the computer constraint. although the computer solution, even using Excel, will allow us to have more than 2 decision variables. Now we're going to describe each constraint. We're going to limit it to 4 for our class. Again, there can be thousands. All right, so let's walk through this again. I'm going to recite from the text. Par Inc. is a manufacturer of golf equipment, and they've decided to move into the market for medium and high-priced golf bags. And they're going to call these bags the standard bag and the deluxe bag. Now, again, it's section 2.1 on page 32. They understand what it's going to take to build these bags. They know that there are 4 sets of steps: the cutting and dyeing, the sewing, the finishing the material, and then the inspection of packaging. So manufacturing department has developed an estimation of how much effort in terms of time and hours it takes to complete each type of bag, the standard bag or the deluxe bag. And there's a table, 2.1, at the top of page 33. And that is their estimate, 0.7, 0.5, 1, 1/10, and so on. So back down to the bottom of page 32, there are constraints. They know that they only have a certain number of hours available in a given week. Pardon me, for each period of time, in this case, during the next 3 months. So they've got 630 hours for cutting and dyeing, 600 for sewing, 708 for finishing, 135 for inspection, packaging, and so on. Now, the last paragraph at the bottom of 32, accounting has analyzed and understood what the profits are going to be, and profits in this case are going to be given as $10 per standard bag and $9 for deluxe bag. So the instruction tells us, let's develop a mathematical model that can determine the number of standard bags and number of deluxe bags to produce in order to maximize total profit contribution. Okay, so I have actually jumped ahead a little bit. I've given you my graphical screen capture of what I've done. But again, looking through the text, we have these constraints, we have the objectives. We're going to identify variables of S on the bottom of page 33 to be the number of standard bags. We're going to allow D to be the number of deluxe bags to produce. And we're going to say, what is our objective? We're trying to maximize. They told us, maximize total profit contribution. We know that each standard bag brings $10 profit. We know that each deluxe bag brings $9 profit. So total, that's how we express the objective function. The objective function is max 10S plus 9D. Now let's identify the constraints. We're being told that, again, per table 2.1, each standard bag requires 7/10 of an hour, 1 hour for a deluxe bag, and that there's a constraint for how many cutting and dyeing hours there is allowed. That's 630. So I will write that. First constraint is 0.7 S plus D must be less than or equal to 630. We do the same for each of the other constraints relative to sewing and finishing and inspection and packaging. These are our 4 constraints. Now, S and D, we're going to say the non-negativity constraint, S and D must be greater than or equal to 0. What I'm highlighting here in handwritten form is also in your textbook in a table on page 36. Now, the text will go through on pages 34 and 35 exactly how to set that up. They're just going to take in longhand form what I've just recited to you in quick form. So hopefully you're able to follow along. We can do another particular setup of a problem, and I'm going to do that next for problem formulation in another segment here. I'm going to end this first segment at this point in time at slide 10 after 15 minutes when I'll record another segment. Thank you.